This video covers Learning Outcome 2, which is about good experimental design. At the end of this video, my hope is that you'll be able to describe 3 qualities of good experimental design. And the way we'll do that is I'll outline them for you, and I will talk about a specific experiment that had excellent experimental design. So this is the Salk vaccine experiment. In 1954, this experiment was designed to test the effectiveness of the Salk vaccine for preventing polio. It had killed and paralyzed thousands of children. By random selection, 401,974 children were randomly assigned to 2 groups, the treatment group, which was given the vaccine, and the placebo group. So we're going to see that this is an excellent experiment. It had excellent experimental design. And it had excellent experimental design because of this one quality. Good experiments have or exhibit replication. Now, when Triola uses the word replication, he means it in this way. He's talking about the repetition of an experiment on more than one individual. So when there are about 401,000 children in the Salk vaccine experiment, we know that that has been replicated. We didn't just give the vaccine to one kid and say, oh, did it work for you? Well, then it must work for everyone. They gave it to approximately half of 400,000 children. So that sample size was very large. So we can say that that experiment was replicated. Now, sometimes in other settings, you'll see the word replication referred to in experimental design in this way. They'll be talking about the repetition of an experiment, by multiple researchers. So this graphic at the bottom is one that came up whenever I searched for replication online. See how all of these scientists are sitting at different desks, all of them repeating the same experiment? Well, that is something that we can think of as replication as well. But when Triola uses the word replication, he's talking about repeating the experiment on more than one individual. So he's talking about sample size. Larger samples are better because if you have applied a treatment to 200,000 people, that's going to give you a better sense of whether or not it works than if you apply it to one person and then you just look for the effect on that one person. So again, this just is talking about sample size. Replication requires sample sizes that are large enough to show us the effect of treatments. Good experiments also exhibit what's called blinding. And blinding is when the subject doesn't know whether or not he's receiving the treatment or the placebo. If you tell somebody that they're receiving the treatment and they know that they're supposed to get better if they receive this treatment, they might behave differently because they know what you want, or they know how you want them to behave, or they perceive that you would prefer you, the experimenter, or the person who is administering the experiment. They seem to think that they know what you want, and so they'll try to give you what you want. And if they're receiving the placebo and they know that, if they know that they're not receiving the treatment, then they'll sometimes act as if it doesn't work because they know it's not supposed to work. So we don't want people who are participating in the experiment, our experimental subjects, to know whether or not they're receiving the treatment. We want them to actually experience what happens to them and then report it as honestly as possible without their own biases getting in the way. So that's why we use this technique of blinding, where we don't tell the subject whether or not they're receiving the placebo or the treatment. If we're talking about this polio vaccine, both of them are getting, children in both groups are getting a shot, but we're not telling the child and we're not telling the parents whether or not they're receiving the vaccine. So that's what it means to use blinding in an experiment. Good experimental design includes blinding. And this allows us to get around the placebo effect, which occurs when an untreated subject reports improvement in symptoms. So sometimes, if they're not being treated, but they think that they're being treated, they will exhibit like a lessening of symptoms or a positive outcome, even though just the thought of them being treated is affecting them and not the medicine or the treatment itself. I love this little image that I found online. This is not what we mean when we say a double-blind study. I'll tell you what a double-blind study is on the next slide, excuse me. So you've got a couple of experimenters, couple of scientists like spilling things in the lab, and they're both blindfolded. That's not what we mean. Okay, so double-blind is when blinding occurs at 2 levels. So the subject doesn't know whether or not he or she is receiving the placebo. And we're just asking them to report as well as possible what's happening to them, without the bias that would be, I want to say incurred, but I'm not sure if that's the right word, but without the bias that would happen or occur due to knowing that they were receiving the treatment or the placebo. But a study is double blind if the subject doesn't know and the experimenter that is applying the treatment doesn't know. So sometimes, even if the subject doesn't know whether or not they're receiving the placebo or the treatment, the experimenter will treat people in the placebo group a little differently than they treat people in the treatment group. And of course, this is typically unintentional. It just happens because they know. They are giving things away in their tone of voice and their body language and the way they treat the subjects without even realizing it themselves. So in order to prevent that from happening, the experimenter doesn't know and the subject doesn't know. So we call that a double-blind study. So I love this. Again, you've got your double-blind study on the side over here. These guys, this is not what we mean when we talk about double-blind, like nobody's wearing blindfolds. It just means that the subject doesn't know whether they're receiving the placebo or the treatment, and neither does the person that is administering the treatment or the placebo. And I think that this little quote at the bottom is cute. Was it a replicated study? Was it a randomized double-blind study with treatment and placebo groups? Because if it was, that's a very good thing. Okay, so far, 2 qualities of good experimental design are replication. So the experiment has been done a number of times on a number of subjects. And then there's also blinding. Typically, double blind is better than just blinding the subjects. We don't want anyone to know whether they are receiving the treatment or placebo, or whether they're administering the treatment or placebo. We want to help keep everyone as honest as possible and unbiased as possible as they report on their experience with this treatment. The third quality of good experimental design is randomization. So this means that subjects are assigned to different groups through a process of random selection. The polio study had subjects assigned in this way. They didn't flip a coin, but they may as well have flipped a coin to determine whether the child would go into the treatment group or the placebo group. That's random selection. The rationale is if we randomly assign people to groups, then by using chance, the 2 groups that we created are likely to be very similar because we haven't unintentionally grouped people that are similar in one group and similar people in another group. We just sort of randomly assign everyone everywhere. And it might seem a little bit counterintuitive to do that, to use something random to create similar groups, but actually that's what we do, and that's exactly what happens. Usually random selection does result in similar groups. Now this idea of using a randomized design with placebo and treatment groups, they call it the gold standard because it's so effective. So generally this is what you want to do in an experiment. You want to have people randomly assigned to 2 or more groups, and you want to have treatment groups and at least 1 placebo group or 1 control group to see if that treatment is actually causing the effect that you think it is, and then measuring that effect from there. So this Salk vaccine experiment from 1954. Let's think about whether or not it's a good experiment or not. Well, it says by random selection, these children were randomly assigned to 2 groups, a treatment group and a placebo group. So we've got replication because there were 401,974 children participating in this experiment. So we ran this experiment 401,974 times, if you will. We can think of half that if you were saying every experiment consists of 2 kids, a control kid and a treatment kid. or a kid in the control group and one in the treatment group. So there's replication there. Sample size is large enough. It was double blind. The children and their parents didn't know, and the person administering the injections didn't know whether the child was receiving the vaccine or not. Excuse me. And then lastly, there was randomization because the children were randomly assigned to two groups. About 200,000 were treated and about 200,000 weren't treated. So this is an excellent experimental design. If any parts of this are missing, well, then there's something to consider. We might want to improve the design before we replicate the experiment and try to do it again. So you want to make sure to keep replicating. You want to have a large sample size. Also, the experiment should be, we should be able to replicate it. Other scientists should be able to replicate it. That's another use of the word replication. It should be double blind if possible. And people or subjects should be randomly assigned to groups, or if they're not people, the experimental units should be randomly assigned to groups to have an excellent experimental design.